talk about wait, let me check. Okay, so I will talk about so first just the beamline, the P08 beamline at the PETRA III. So we are a high energy synchrotron 6 GeV ring like argon. Used to be quite low emittance synchrotron, but now we are surpassed already by several fourth generation one, including the APS-U upgrades. So first I will talk about the beamline, and then I will put the focus into the Langmuir trough grazing incidence diffraction setup. So one of the three major setup at this beamline, and then also talk about the recent theory development for the liquid surface scattering, and also the capability of acquiring the reflectivity from liquid surface by doing single shot GISAXS measurement. And in the end, I will also talk about a little bit near future development that we are doing at this beamline. So we are amongst several diffraction beamlines in PETRA III, but the name is high resolution diffraction beamline, but we are certainly not a powder diffraction beamline. This is usually what where people get confused. So our beamline operates in the energy range between 5 and 29 keV, but usually we work at several chosen energies, so 9 keV, 15, 18, and 25 keV. We have a very parallel beam with a very small energy spread. So if one used the normal beam size between 30 micron up to 500 micrometer beam, we have a very low divergence. So 10 microradian in horizontal and 2 microradian in the vertical direction, with a energy resolution of 10 to the -5. And that gives us a very high Q resolution that allows us to look into very small structure change due to this Q resolution. And then, but because of this very high resolution, we actually do not have that high flux. So the flux is usually 10 to 11 to 10 to 12 photon per second. At our beamline, we mostly focusing on surface diffraction. So that means the scattering and diffraction from both the solid surface and also liquid interface and surfaces. For all the solid surface experiment, we do that on a 6-circle diffractometer, and so the soft matter interface user usually measure things on the solid liquid interface or hydrated multi-layers on solid substrates. And then here we have the beamline chamber come from the collaboration with the universities in Denmark and also in and CMU from US. But also we have also sample stages for traditional hard condensed matter surface studies. We have two instruments for liquid surface diffraction. One is the Langmuir trough GID setup that is optimized for the grazing incidence scattering experiment only on Langmuir trough, so very specialized setup. And the other one is a general purpose liquid surface diffractometer. It's LISA, that is provided by the University of Kiel under the funding from the German Ministry for Research. And this one uses the double crystal beam tutor concept, and was so Bridget Murphy already introduced that I think a month ago in the last seminar. So today I will focus on the first instrument. So this Langmuir trough GID setup, as its name suggests, is only using a fixed incidence. So we fix the energy to 15 keV, and then it operates at 85% of the critical angle, which is 0.07 degree with respect to the horizon. And then it does only the grazing incidence scattering experiment, so the wide angle and small angle scattering, and also the X-ray fluorescence measurement under the total reflection condition to look into the accumulation of the elements at the interface. And because the incident angle is fixed, we actually could really put the beam transport line into vacuum using a mirror to bend down the beam and then let everything passing the vacuum tube until the trough. So here you see the enclosure of our Langmuir trough, and everything the beam is transported in this vacuum line. And then in the trough, we actually also can easily put a pinhole before the trough, but after the entrance window to clean up all the front end backgrounds. And then after the trough, we can also put a beam stop before the exit window such that we prevent the beam to hit on the exit window to create background scattering. So in this way, we really suppress the background noise as low as possible, and then that allows us to get very high quality grazing instance scattering data from this setup. Within the enclosure, here you see here you see the cut drawing of our Langmuir trough on the base plate, and this Langmuir trough is a customized trough from Kibron company, and then we provide several the trough plate with different sizes, and this trough is then mounted on a independent translation and high translation that is independent from all the components like a pinhole and beam stop, or from the fluorescence detector. And here you see some example data that we get. So here you see the wide angle diffraction data from the Langmuir trough. So this is lipid monolayer. In this case, is a fatty acid monolayer with a perovskite growing below that. And this is a typical GISAXS pattern from a nanoparticle monolayer. And here you see the fluorescence emission from the bromine, and also from, I think here they put some, I don't remember what is the emission here, from the Langmuir monolayer. And these are the typical data quality that we can get from this setup. Okay, now the users who wants to measure the GID data or GISAXS data from this setup often also says, can't you also provide the layer structure? We cannot do reflectivity because otherwise we have to tune the incident angle, and then this is not compatible with all the pinhole and beam stop settings in this setup. However, as people from your group also knows that using the GISAXS geometry, one can also get the layer structure information. So here you see a typical GISAXS image that we get from a lipid layer, and in this case a DPPG phospholipid monolayer. And this is the vertical direction, and then here and the horizontal is and then this is the horizontal direction. So taking the line cut somewhere away from the specular plane gives this oscillation that you can see in this plot here, that almost mimicking the liquid surface structure factor from a monolayer. However, with then this oscillation, the amplitude of the oscillation depends on the off-specular, the angle away from the specular plane. So now the question is, how does this off-specular scattering data or curves relate to the structure that one usually gets from reflectivity, from liquid surface? And this is something that we solve in the end by looking again into the liquid surface scattering theory. So on this liquid surface on the liquid surface, it has a roughness that is due to the thermal fluctuation, and this is so the topology of the surface due to this thermal fluctuation is usually described by the temperature, the surface tension of the liquid surface, and also the stiffness of the thin film on top. And then from this so-called power spectrum density that is given here, one can derive the scattering amplitude for both the reflectivity and also the diffuse scattering around the reflection peak. And remember that when one measures the GISAXS data from the liquid surface, we are actually measuring the diffuse scattering around the total specular reflection peak that is blocked by this beam stop. And this scattering formula for both the reflection and also the diffuse scattering is given by the same formula. So it consists of 4 contributions. The first 2 contributions here corresponds to the subphase. So this is the critical angle of the air-water interface in this case. And then the second contribution is the intrinsic structure factor that is related to the electron density profile along the z direction, assuming the surface is purely flat, no thermal roughness. And then the last contribution, this roughness factor, is then related to the power spectrum density of the thermal roughness. So this describes the topology, or is related to topology that is generated by the thermal fluctuation and is related to the surface tension, temperature, and the bending rigidity of this thin film on top. And here you see the expression of this roughness factor, and it has two terms contributions. One is only the tension term, and that is basically the standard capillary wave model. And then the second term is related to the stiffness, so related to the bending rigidity. So when there is no bending rigidity, so the bending modulus equals to 0, then this roughness factor is reduced to a standard capillary wave model expression. So the intensity of the scattering as a function of the QXY drops as a power 2 to minus eta, where the eta is related to the surface tension. So this is this straight line. And then the reflectivity, it becomes also the well-known factor where you have this roughness factor term that can be simplified into an exponential decay. And the factor in the exponential decay as a function of QZ is given by this thermal roughness that is related to the in-plane resolution in the reflectivity measurement. And then this is then modified by a power of eta here. So this is then given by this dashed black line here. This is what we usually know as the capillary wave model. So now what happened when there is a bending rigidity? So the bending rigidity provides then the second term, which is a negative modification to the standard capillary wave fall off. So instead of having a straight line in the log plot as a function of QXY, we have this additional drop here. So this is described by this black line behind. And then eventually it reaches QXY to the -4 dependence. And for the specular reflectivity, then this modification given by the bending rigidity then basically changes the cutoff of the in Q from the Q max that is related to molecular size now into a value that is related to the stiffness. So to put it into a phenomenological description. So basically, this is equivalent of changing the size of the molecule to a bigger size, because when the surface is more stiff, then it cannot really be bended in at the molecular level, but has to be the fluctuation only occurs at a larger length scale. And then in the roughness factor modification to reflectivity is no longer this drop given by this dashed line, but have a less drop. So this is then given by this solid black line. So basically, the stiffness makes the reflectivity higher compared to a surface without the bending rigidity. So this formula here, or this as we now call it extended capillary wave model, give us then the possibility to fit the GISAXS data from the liquid surface, because it gives already a QXY dependence. So this is then given as a modification to the standard capillary wave model. So here the black dashed line is the predicted QXY dependence of the diffuse scattering by the capillary wave model, which is without stiffness. And our data here measured from DPPG lipid monolayer shows a deviation, negative deviation. And by fitting this negative deviation, we can get the estimation of the bending modulus, which is 15 kT in this case. And this is measured at 35 milliliters per meter surface pressure. And then, because we know the surface tension from the tensometer and temperature and also the resolution in the diffuse scattering measurement, which is given by the pixel size of the detector, we were able to really compute this roughness factor contribution for the diffuse scattering or for this GISAXS pattern. And that allows us to use this formula to derive the intrinsic roughness, the intrinsic structure factor. And then this is then this data showing on the top. And remember, this intrinsic structure factor corresponds to the electron density profile along the z direction, assuming there is a perfect flat surface. So this is then related directly to the the distribution of the chemical moieties along the z directions, instead of the average data being broadened by the thermal roughness. And this is now given by this dashed red line. And getting this intrinsic structure factor has an advantage that one can now really clearly see it, now the hydrocarbon layer and also the phosphorus head group layer from the phospholipid monolayer. So one can really distinguish the two layers much more clearly, and then this the width of each interface between the slabs directly corresponds to the distribution of the chemical moieties, like this transition from the hydrocarbon region into the phosphorus head group region via the glycerol back bond. Stephanie, you are muted.
Oh, sorry. Can I ask a question here? So you looked at different distances from the center, from the meridian, and you have the different curves corresponding to. We do a similar thing, but I mean, I'm wondering, what was your ideal distance from the center to match any literature values of head-to-head spacing, for example?
Actually, it's not from the center because it's a monolayer. So we actually measure from the top surface of the air tail interface all the way into the water. So one side is air, the other side is water. So this is on the liquid surface.
Yes, I understand that. But I mean, in the figure that's all the way on the left, you have a white line in the center. That's what I'm talking about.
Oh, this is the specular, the plane of the incidence of
I know.
of the measurement. Yeah.
I know. But then you had different lines going out to different degrees. In the last slide it was, I guess you had some vertical lines at different distances. I thought that was seen here in the in the figure right next to the one on the left.
That is correct. We choose 4 line cuts here as an example.
So, I mean, of those different distances, which one is the preferred one for you to get the structure?
Oh, actually, this is a joint fitting of all the differences. So 4 differences we pick up at the so we pick up basically where the scattering is the strongest, because that gives us the highest signal noise ratio for the diffuse scattering. So then we pick up 2 lines here and then 2 lines here, and then does the fitting in with all the 4 data sets.
Let's see. Okay, good. Thank you.
Yeah, and actually, then what we get here is only the bending modulus. Then we put the bending modulus back into the this analytical formula for the roughness factor, and then together with the angle and the angular resolution of the detector pixels. And by that, we can compute the contribution of the roughness factor for every QXY and QZ on this detector image. And by that, that allows us to calculate the roughness, the intrinsic structure factor for actually different off-specular positions. But here what you see are actually the overlaying intrinsic structure factor from 5 different off-specular positions. They just lie on top of each other. So the analysis is independent on where one does the off-specular line cut to get the structure factor.
Thank
So
you.
otherwise, that would, if that would not work, that would mean that our theory would be wrong. Yeah. So, and then that's how we ended up with this intrinsic structure, because we get the structure factor, and then that also give us an opportunity to really know the contribution of this roughness factor. Okay, now you might wonder, so what is this black line and then the orange data here? I will show you in the next slides. So remember that the diffuse scattering and also specular reflectivity are described by the same formula, with the only difference that the QXY for the diffuse scattering is not 0, and for the specular it is 0. And that basically means that there is an analytical formula that describes that relates the diffuse scattering intensity to the reflectivity at the same QZ. And this is basically the ratio of the two roughness factor, one at the off-specular position, one at the specular position. And then one can derive that. And once one knows the bending rigidity and also the resolution of the diffuse scattering measurement in the GISAXS, on the GISAXS detector, one can assume any in-plane resolution for reflectivity, and then by this formula here, derive the reflectivity for that in-plane resolution. And this is what we get. So we take the bending rigidity that we get, and then calculate this the analytical formula for the of this ratio, and then afterwards compute the specular reflectivity for a resolution of 0.0002 inverse angstrom in the in-plane direction. And then, since this is not really measured by under theta to theta geometry, we call that pseudo reflectivity. And this is this, and then this orange line, and then we also can compute what is then the roughness contributed by the thermal roughness, because that is basically the log of the roughness factor divided by the square of the QZ. And that is related to the bending rigidity. And then this roughness is given here. So that is about 3.4 angstrom for this DPPG monolayer at 35 Newton per meter. And if one assumes 0 stiffness, then the capillary wave roughness would have been 4 point something angstrom at this surface pressure. So this already tells that the stiffness reduce the thermal roughness, because now the surface, especially at high frequency, cannot be bended due to the thermal fluctuation anymore. And in addition, what one actually gets, the structure that one gets from the specular reflectivity is a convolution between the intrinsic structure that is given by the chemical moiety distribution with the thermal roughness profile. So all the interfaces is smeared out. And that is also why usually if one just measure the reflectivity under theta to theta geometry and do not precisely know what the thermal roughness contribution is, one always get this very smeared out structure, and then do not get very high spatial resolution. And also when one measure a monolayer of softer matter on a liquid surface, without explicitly measuring the diffuse scattering and knowing what is the contribution of what is the value of this bending rigidity, one also cannot really estimate get the intrinsic structure factor and the intrinsic structure, because one would not be able to estimate what is the precise thermal roughness without knowing this kappa. Okay, now the question is, how does this derived pseudo reflectivity compare to the real reflectivity? Here we did a verification experiment on the exact same film. So we measured DPPS film at, if I remember correctly, 45 Newton per meter. And then we did the off-specular measurement, and then derived, so basically diffuse scattering and derive the pseudo reflectivity. But in this case, we use the resolution of a rectangular slit for reflectivity. And then we also measure the reflectivity under the same resolution, so 1 millimeter times 1 millimeter at 1 meter. And then the black line is the reflectivity measurement, reflectivity obtained from theta to theta geometry, and the red one is then the pseudo reflectivity that we derive from this diffuse scattering measurement. And you can see that both data just agree with each other. So that means that the pseudo reflectivity that we can get from the diffuse scattering measurement really agrees with the reflectivity that one gets from the traditional method if one take into account this bending rigidity. And this bending rigidity of 20 kT is obtained also from the diffuse scattering on this exact same sample, but with the QXY dependence measurement. So we take the diffuse scattering at different off-specular position and fit the deviation from the capillary wave model with this formula of the roughness factor here. So now you also see that the pseudo reflectivity that we get from the diffuse scattering measurement extends to a larger QZ. So now at our Langmuir trough GID setup at P08, we have a really low background because of all this pinhole and beam stop setting here. And for that, we actually can reach 10 to the minus 13 dynamic range. So this is now stopped at 1 inverse angstrom for this data set after 30 seconds of acquisition. And I can tell that this is not the end of the data that we can get. We only measure up to 1 inverse angstrom because our detector is that big. Now we have Eiger 4M, so we hope that we can see something further. Because once we actually accidentally put the detector closer and we still see a diffuse scattering up to 1.2 inverse angstrom, so it's not ending. And the conventional reflectivity usually reaches 10 to the minus 10 instead. So in the end, so I hope that you are kind of convinced that one can obtain the reflectivity under the by measuring the off-specular diffuse scattering, and then the data agrees with the specular reflectivity that one gets from the traditional method. However, because we are working with the grazing incidence condition and by that reduce the bulk scattering contribution, we are able to reduce the noise and then reach a higher QZ range and also a better dynamic range. And also this, since one can measure the QXY dependence by doing the diffuse scattering measurement on the off-specular geometry, one can also get the bending modulus of the surface, and by that also obtain the intrinsic structure factor and separate the thermal roughness out of it. And then at P08, we currently do not provide directly the diffuse scattering data to our user because most of the users do not know how to handle that with this theory. So we have a data pipeline that provide them the fitting of the bending modulus. So they get a bending modulus and also the value of the thermal roughness and also the intrinsic structure factor. And in addition, what they get is the intrinsic structure factor times RF, such that they can use the reflectivity software to fit that data. And they also get directly the pseudo reflectivity curve that they can also fit with the traditional reflectivity analysis software, while at the same time allowing them to compare that with the specular reflectivity that they get from other reflectometers somewhere else. For example, many users have the lab source, so they can measure up to 0.5, and then they can directly compare that reflectivity with the diffuse scattering data that one gets here by comparing the pseudo reflectivity. So this is what our user usually get from our Beamline now, if they come to this Langmuir trough GID setup. So now you see what we can do for now. And I want to spend a little bit time talking about what we are expecting, let's say, that within the next 12 months. So one of the things is that we used to have we actually used the Eiger-1M detector from Bridget's group from Kiel University, and that limited our QZ range to 1 inverse angstrom. And now we get a new detector. So it's the Eiger 4M that covers 2 inverse angstrom times 2 inverse angstrom in reciprocal space. So that allows us to, for example, look into the pipette stacking in peak if people do some conjugated polymer layer on liquid surface. And also we now expect also a 1D lens for microfocus option down to 3 micrometer, and that would allow us not only to measure smaller sample with a smaller Langmuir trough, but also that allows us to do one-shot grazing incidence diffraction experiment with the 2D detector without the solar collimator. So that would be suitable for really time-resolved measurement or operand or in situ measurement. Then we also want to really provide a maintenance-free automation. That means changing the thin film on the liquid surface and changing the whole subphase in the Langmuir trough in the automated fashion, but with the maintenance. But that should be free of maintenance. So we have had already a prototype that demonstrates this is possible to really swap the film and then change the subphase. And now we, with the collaboration with the Kiel University and also Lund University and the European Spallation Source, we want to upgrade that into really a maintenance-free version. We also, some times ago, we have a really strong corrosion of all the motors in our Langmuir trough setup because people bring in some very aggressive chemicals for their experiment. And now actually we are building a second enclosure inside our Langmuir trough GID setup to protect all the other motors, because you can see that we have all this pinhole and beam stop to reduce the background, but that also make the whole setup quite let's say vulnerable. And then but we hope that we can find a way not to compromise too much the data quality, because of course the sub enclosure means that we have additional windows, and then we have to figure out a way how to then still do the same low background GISAXS measurement with the sub enclosure. And of course then we are also very welcoming the collaboration, and that means donation of manpower and equipment or sample or programming efforts from anywhere. So in the end, I want to still say that this whole development and also the Beamline that equipment that I show were supported by many grants, but also a lot of people who contribute to these studies, especially I mean my colleagues from P08 and also from DESY, but also here for the this extended capillary wave model, Ben Oko and Honghu from Brookhaven National Lab has contributed a lot with all this theory development, and also we did the measurement together to prove that the two reflectivity are really consistent with each other. And then we also get a lot of support from many colleagues. And then also the since I mentioned P08, so we have a second liquid surface diffractometer, LISA, and also associated with a laser instrument on top of that. And this is then provided by the Kiel University. Yeah, so that's it. And